All right, so here's our practicum problem for tonight. We've got some structural design problems trying to figure out areas and numbers of rivets. So we'll start off with the first one here. We've got a beam loaded in tension. We have 15 kips as the applied load. We've got several situations to consider. One is if we let the beam be loaded up to its ultimate stress. So we'll figure out the minimum amount of area needed to do that. Then we'll reconsider whether it's a good idea to load it up to its ultimate strength and load it only to yield. And then we'll apply a safety factor and see what area that gets us. So the fundamental equation is our definition of normal stress. More often than not, with working with strength of materials problems, if you don't know where to go, start with your normal stress equation. And if it's a normal stress problem, if it's a shear stress problem, start with the shear stress equation. But it's always going to involve stress, force, and area. You just have to figure out what you've got and what you need to solve for. So in this case, we've got a load or a force of 15 kips. We don't know how much area we need, but whatever area we use, it should load this beam all the way up to the ultimate strength, which, according to the table here, is 70 ksi. So we're looking for 70 ksi of area. We won't have unit issues as long as or 70 ksi of stress. We won't have unit issues as long as the prefix lines up here. So pounds and psi, kips and ksi. If we cross multiply, we'd have 70 times A equals 15. Divide both sides by 70. So 15 over 70, the units will work out to be square inches. And our number, 15 divided by 70, that'll be a little bit less than a quarter square inch, so 0.21429 square inches. So a little bit less than a quarter of a square inch. So not a lot of material needed as long as we're willing to live on the edge of this thing breaking. If that's a little bit too close to the limits, we might consider backing off to the yield strength, because if we did apply that much force and drive the stresses that high, this thing would definitely yield. This thing would stretch out by some amount and have a permanent strain. So to figure out what would happen if we only load up to the yield stress, which is our part B of problem 1, we again start in the same place. The normal stress is force divided by area. We have the same force of 15 kips, but this time we're only going to let the stress climb up to 50 ksi. So we'll need a bigger area. Bigger area will give us a smaller stress. So again, cross multiply. We have 50 times A is 15. Divide both sides by 50. And A is going to be 15 divided by 50, 0.3 square inches. So larger amount of area, but now we're just sitting on yield. We're just on the edge of this material, stretching out permanently. As long as the force never goes up above 15 kips and the material never weakens, there's no corrosion or anything like that, or cracks that might form, or physical damage that might reduce the area somewhere, then this thing will never change shape permanently. But if we want to build a little bit of a safety factor in there, we have the option to do so here. In this case, we've got specified a safety factor of 1.25. Now we can either use the safety factor to increase our force, or we can use the safety factor to decrease the yield strength, since they ask us to load it to yield with that safety factor of 1.25. So since in the lecture I applied the safety factor to the load, I think here we'll apply it to the yield strength. Remember, the fundamental application of the load of the safety factor. It multiplies the load, but it divides the strength. We assume the material is either weaker than it actually is, or we assume the load is bigger than it actually is. So this time I'll correct my stress. So the stress here we want is 50 KSI, but I'm going to divide that by 1.25. If I divide that by 1.25, I should get a relatively nice number out of that, because dividing by 1.25 happens all the time. It's actually the same thing as, 50 divided by 1.25. It's the same thing as taking 80%. Dividing by 1.25 is the same as reducing to 80%, and that gives us 40 KSI. So here we're going to assume the material is weaker and that it can only handle 40 KSI before it yields. We're going to need a larger area to make sure we don't hit that reduced strength. So again, normal stress is force over area. We've got a force of 15 kips. We didn't alter the force this time. We altered the strength of the material. So we're assuming we're only going to hit 40 KSI. So cross multiply, and the area is going to be 15 over 40 square inches, which is 0.375. So to load it up to the ultimate stress, we needed an area of 0.21429 square inches. To the yield stress, we needed 0.3 square inches. And now for the corrected yield strength for a safety factor of 1.25 to essentially stay at 25% away from yielding, we have 0.375 square inches. Any questions on any of those? All right, let's try the rivet problems here. Now, I actually did get real data for these. I pulled up my copy of the machinery handbook, which I happened to find on one of my shelves back here. And these are the actual, this is the actual shear strength for AD rivets and for DD rivets. AD rivets made out of 2117 aluminum, 28 KSI. DD rivets have a strength of 42 KSI shear strength. So we'll work a couple different materials and different diameters. So as always, go back to the fundamental equation. In this case, shear stress is force over area. Well, we want to find out how many rivets we need, which essentially is how much area we need to keep this thing from breaking. It's going to break at this shear stress of 28 KSI. So our stress is 28 KSI. We're told we have to support a load of 8 kips. So we have 28 KSI and 8 kips divided by the area. So that'll tell us how much area we need from a material that can handle a maximum of 28 KSI. So if we cross multiply, the area will be 8 over 28, again, square inches. And so you have kips and KSI lining up. So you have 8 and 28. So that's going to be 0.28571 square inches. But we're not done yet. We can't stop there. The problem wasn't how much area of 2117 aluminum do we need to prevent this connection from shearing. We need to know how many rivets we need at a minimum. Rivets have to be a whole number of rivets. So we have to figure out what the area is from one rivet and then divide that into the area we need. And that'll tell us how many rivets in total we'll need at a minimum. And if there's any fractional rivet, we have to go 1 rivet higher. So we'll find the area of 1 rivet. We're told that that is an 1/8 inch diameter rivet. So we have pi times 1/2 of the diameter, so 1/16. squared. So we'll square that, multiply by pi, and we get 0.012272 square inches. The number of rivets is the total area over the area for one rivet. So if we divide those out, 0.28571 square inches, and we divide that by the area of one 1/8-inch diameter rivet, that'll tell us how many rivets we need. So 0.012272. We have 23.281, which we'd have to bring up to 24. So we need 24 rivets to handle that load. So 24 rivets at a minimum. Now, of course, that assumes that those rivets are spaced far enough apart that we don't have structural issues, the stress concentrations in between the rivets, and that they are far enough away from the edge of the material. Other details that we'd have to bring in a real sheet metal lap joint design. But to satisfy the strength requirement, we'd need 24 rivets at a minimum to do that job. Any questions on that one? And for our last one here, same load, but now we're dealing with 1/4-inch diameter rivets and a stronger rivet. So let's try and predict where this one's going to go. We're dealing with a stronger rivet at 42 KSI. So we're not going to need 24 of these. Even if the diameter was the same, if we went with a stronger rivet, we could get away with fewer of them. These are also bigger rivets. These have twice the diameter, which means it's got 4 times the area. So these are bigger rivets and they're stronger. So we're not going to need very many of these at all compared to 24. So that's a prediction on where we'd be. To calculate it, go back to the equation. Shear stress is force divided by area. We still have to handle a force of 8 kips. We don't know how much area we need, but we're going to pick an area, so we're just going to max out the material and hit 42 KSI. Cross multiplying, the area would be 8 over 42 square inches, which is 0.19048 square inches. Now the area of one 1/4-inch diameter rivets, pi times the radius squared. The radius of a 1/4-inch rivet is an 1/8 inch. So we'll square that and multiply by pi. And we get 0.049087 square inches. The number of rivets is the total area divided by the area of one rivet. So we have 0.19048 square inches that we need. Each rivet's going to contribute 0.049087 square inches. So 0.19048 divided by 0.049087. And that comes out 3.8805. I think I'll just leave it at 3.88 since I know I'm going to have to go to 4. So it's only going to take 4 rivets to do the same job in that situation. Stronger rivets and larger area. Any questions there? All right. Have a good night.